All right, so yesterday we talked about formation of ions. We dealt with metals, and we talked how the metal atoms tend to lose their electrons in order to achieve that full outer shell. We talked about how maybe in the past that a teacher might have said that it's much easier for it to lose 2 than to gain 6, but in actual fact it really doesn't have anything to do with ease, and it doesn't have anything to do with a desire to get a full outer shell. The laws of physics govern how easily an atom has its electrons taken away, all right? And it turns out that these atoms are big, and so the electrons are far away from the positive nucleus, so the force to take it away is really weak, and so it's easier to have the electrons taken away. The nonmetals, you might say, oh, they've got 7 and 6 electrons, and so it's much easier for it to get 2 or 1 electron. Again, that's not the case. It has everything to do with the laws of physics. The atoms of nonmetal atoms, they tend to be smaller, and they also, they're smaller. Their outer shells are closer, and so therefore the force of attraction to pull on another atom's electrons is greater, and so it pulls and takes electrons away from other metal atoms. So it has everything to do with the forces on their outer electrons. We also looked at the charges of the ions that were formed, and so previously with our Lewis diagrams we learned that it has 1, 2, and 3 outer electrons, and when it loses those negative electrons, right, it loses the negative charge, man, right, it becomes positive, right, giving away the negative, and so they become +1, +2, and +3 in terms of their charge when they've lost their outer electrons. For the nonmetals, they gain electrons, so the nonmetals in group 4 or 14 will gain 4, they become -4. These guys in 15 gain 3, they become -3. 16 gains 2, they become -2. And 17 gains 1, and they become -1 in charge. Any questions or concerns about yesterday's stuff? Pretty straightforward stuff. Noble gases don't gain any, and so their charge is neutral, all right? Okay, so today we want to put those 2 atoms together, and we want to talk about how ionic compounds are formed. First, let's define an ionic compound. We're going to bring the examples right up here, and I'm not even going to bother with all this animation. We're just going to bring it up. Get that out of the way. I have your quizzes marked. Just remind me at the end of class to hand them back. They're right there. So ionic compounds contain positively charged metal ions and negatively charged nonmetal ions held together by an ionic bond. Now again, we use the term bond to represent something that holds them together, but they're not a physical entity. They're not a thing. It's not that there's a little stick holding these things together, all right? We'll talk a little bit more about that in a moment. Some examples of some ionic compounds. An Na plus with a Cl minus makes NaCl. We don't write the charges because when the ionic compound forms, those opposite charges that hold them together, it's as if they cancel away. Those opposite charges cancel away, and we say we have a neutral compound, sodium chloride, the metal ion with the non-metal ion, okay? We can have a polyatomic ion. We're going to learn about these when we name them in the near future. And this is an SO4. So this is a copper ion. It's actually a copper 2. That's the type it is. And this is a sulfate ion. Did you guys learn about polyatomic ions last year? No? Okay. We will learn in the very near future that there are ions that are made up of more than one atom that is bonded together. All right. So so the ion is like a larger structure made up of a handful of atoms. This sulfate ion, SO4, is made up of a sulfur bonded to 4 oxygen atoms. All right, so we'll learn about those as well. So that also counts as an ionic compound. The copper has a +2 charge, and this combination of sulfur and oxygen atoms, the sulfate ion, has a -2 charge. They cancel each other out, and we have a copper 2 sulfate ionic compound. Okay, and we'll learn more about that in the near future when we start talking about naming. You'll notice it says there for Thursday, names and formulas of ionic compounds. Okay, so ionic compounds or salts. So this again is a little more detail about ionic compounds. The term salt actually describes any ionic compound. Yep.
How do you guys figure this out?
That is awesome. Oh my goodness. You're talking about chemistry in general, aren't you? You're talking about just chemistry in general. It is a long story. It's a long story. You're talking about chemistry and how do you figure these things out? How do we know that an electron is being transferred from the metal to the non-metal? And that's a really big story. That's a long story. Holy cow! And you want it in terms of ionic compounds. You want it right now. You want the answer now. Well, to be honest, I'm thrown back by this question for a moment. Okay. Goodness gracious. Am I going to record this whole babbling thing for no, I'm going to pause the recording since we're going to be off topic for a little bit. Goodness gracious, McGrail. Killing me. I'm recording again. All right. Told you it wasn't going to be easy. Ionic compounds are formed when metal atoms completely transfer its valence electrons to non-metal atoms. Remember, valence just means the outer electrons, all right? This results in oppositely charged cations, the metal ions and anions, which are attracted to each other. The attraction between the oppositely charged atoms are called an ionic bond. Now, don't draw these pictures here. Oh, wait a minute. Where's the pictures come? Next? Yeah, okay, let's go through this. Let's do that example there. And I'm going to do it as a Bohr diagram here. So I'm going to start over here with Na. That's my nucleus, or the nucleus of the Na. 11, right? Plus 11. We're going to go through one set of Bohr diagrams, then we're going to get to Lewis diagrams, which are much easier, right? And what do we got here? We've got 2, what else? 281? 281. And we're going to put that together with a Cl. Cl is 17 plus 17, 2, 8, 7. Let me know if I'm wrong. 287? We're good? And we believe it because of lots of work by scientists, so we're not going to question so much anymore. No, questioning is good, but we're going to buy this theory for a while. Yes, yes.
Are these the ones that we're learning now, are they laws or?
I have never heard the idea of ions as being the law of ions. But you know what? We don't even talk about it as being a theory of ions anymore. So in other words, we've just accepted it to be true. So I would think it would have to have been elevated to law status, even though we don't say law. All right? We just say we have ions. That's the way the world is. And we don't question it so much like you do, right? We just assume it works. But that's good to question. But I'd like to continue now. Okay, so here we go. We're going to transfer this one over to here. All right, so I'm now going to redraw again. Again, I got plus 11, and now I've got 2, 8, and that's empty. And that thing has a charge of plus 1, plus 1. And we also then have 17, and I apologize for running out of space, 2, 8, and I can hardly put that 8 in there. That's an 8, by the way, for those watching at home. 288, right? We catch that? 288, it's got one extra one in there. Become an 8, all right? And that makes it minus 1, all right? That results in a positive 1 sodium and a negative 1 chloride ion. It is an ionic compound, NaCl, called sodium chloride, which is electrically neutral. If you put it together, it's neutral. Notice the name, sodium chloride, because we have a sodium ion. Remember, the metal keeps its regular name, and we have a chloride ion, hence sodium chloride. Okay? Yep. You know what? Put sodium chloride underneath it. Yep.
When you put sodium chloride, the sodium is...
The sodium gives its outer electron to chlorine, and it becomes chloride. Does it make sense? Okay? It doesn't actually give it. In actual fact, chlorine takes it, but it doesn't take it like a person would take something. It's simply the electron is more attracted to the chloride's nucleus than it is to the sodium's nucleus. So it just automatically goes. If given the opportunity, it just goes. Okay? It is electrically neutral. Okay? So the overall thing is electrically neutral. Don't mind these pictures. Oh, here's just a little animation here, and it repeats. So you got to be quick with it. Oh, it's almost hypnotic. It just goes on and on. It never stops. It's painful. Do you see what's happening there? Yeah. Now, electrostatic attraction, what do I mean by that? You don't have to draw this. We'll talk about this tomorrow when we talk about the properties. When you make something like sodium chloride, never ever does it happen just with one sodium atom and one chlorine atom. It happens with billions and billions and billions, because you're going to have a hunk of sodium metal and you're going to have some chlorine gas. And in that hunk of sodium metal and in that chlorine gas, there's not just one atom, there's billions and billions and billions and billions and billions of them. So when the reaction goes, it happens on a chaotic basis. But in the end, you end up with a bunch of sodium plus ions and a bunch of chloride minus ions. And the way they organize themselves are in what we would call a crystal or a lattice. But don't write this down. So you actually end up with repeating ions in this nice regular structure. This is what is theorized to be the structure of sodium chloride, with the sodium being the purple one and the chloride being the big green one. And it's this repeating sodium chloride, sodium chloride, sodium chloride, sodium chloride. They're not held together by little sticks or anything like that. They're simply held together because they've got opposite charges attracting each other, just like two magnets stick to each other, not by little sticks or by glue, but they're held together by opposite poles coming together. Isn't that fun? Right? So if I had like a whole bunch of magnets, this is the princess, no, sorry, it's not princess, it's the fairy case of magnets. That's where one keeps their magnets. So if I had a whole bunch of magnets, they're going to hold together, all right, in some kind of a structure. Now, this isn't quite nice, an orderly structure as this, but they're holding together not by sticks, even though these look like sticks. They're being held together by the magnetic attraction that holds them together. Same thing with this. These are being held together by the opposite charge attraction that holds them together. So they're literally clumped together. They're not glued together. They're not tied together by little strings. They're just kind of clumping together, all right? And that's really what a salt crystal is. It's a whole bunch of oppositely charged ions that kind of clump together and stayed in a nice little crystal, okay? We'll talk more about that later. Okay, let's draw some more ionic compounds with Lewis diagrams this time. Now this is the big thing. This is what I need you to be able to do. This is what our little assignment is going to be on, which you would have had time to work on, except Megan McGrail keeps asking questions. Oh, I just recorded that name. Megan, whoever she is. And killed about 20 minutes. I'm going to have to delete that? No, I'm not. It's just a name. It's true. It's true. In the whole world, probably millions. Okay, so forming ionic compounds with Lewis diagrams. We're going to start by putting calcium together with sulfur. So here's the way we do this. First, start by drawing the Lewis diagrams of the atoms. Oops, I don't want blue. Not that. Calcium. How many dots? 2 dots. Again, they're not together because they're not helium. Only helium and hydrogen minus 1 hydride gets that. Sulfur. Did you do this last year? Oh no, you didn't even do Lewis diagrams last year. Awesome, this is great. How many dots around sulfur? Yep, 6. I would pick on names, but we're in a hurry now. Now look at, oh, this is a match made in heaven. It's perfect. Calcium has 2, sulfur needs 2. I do this with the grade 10s. I do. I have the grade 10s do it. When you get to grade 11, I don't need to see the squiggles. You might even think they're a little silly, but I'm hoping you can imagine that, okay, those 2 are going to go to those 2, all right? Now we're going to draw the ions formed, just like we drew the ions yesterday, except they're together now. So calcium, excuse me, how many dots around it once it's become the ion? Yep, Marissa? 0. Square brackets. And let's go with some hands up here. And charge on that. Charge on it. Abby? Positive 2. It gave away its negativity, right? You were thinking about a hippie there, weren't you? Very nice. Plus 2. And we're not going to put a little plus in between it because literally they're stuck together. So we're now going to draw our sulfur. I'll put the square bracket here. S. And again, hands up. How many dots now around the sulfur after the transfer? Yes, sir. That's the charge, but how many dots go around it? 8. 1, 2, 3, 4, 5, 6, 7, 8. Negative 2. That is the Lewis diagram for calcium. What's the name of this particular thing? What's the name of this? What do you got? Yeah, very good. I'm going to put it, well, I guess I can stick it in here. Calcium sulfide. I have to say it that way or I spell it wrong. And notice we used 1 calcium and 1 sulfur. So its formula is CAS. Now, I'm going to do a bunch more examples, and again, it's going to say chemical formula and name. You don't have to write that down each time. I think we know which is the formula and which is the name. All right, are we okay with forming those? Let's now do some trickier ones. Lithium and oxygen. Again, when I give you a second example, if you think you know how to do it, use a pencil. Go ahead of me. Lithium, find the number of dots. Oxygen, find the number of dots. Nice. So like I said, don't wait for me. Now then we've got to do some logical thinking. I'm not going to ask because I'm hoping you've all started to do this type of a thing. You can check me. Am I right? How did I do? Thumbs up? Thumbs up from Mr. Sanders? Allison, you going to give Mr. Sanders thumbs up? Thanks. Not a match made in heaven. Lithium has 1 to give. Oxygen needs 2 electrons in order to be happy, right? Which we know isn't the case. Keep in mind, when a reaction like this takes place, never ever is there just 1 lithium atom together with 1 oxygen atom. You would have a hunk of lithium metal, which contains billions and billions and billions and billions of lithium atoms, and you'd have oxygen gas, which contains billions and billions and billions of oxygen atoms. So you're never left with just 1. So I can group these in whatever amounts I need to make everything work. What am I going to do? Yep. 2 lithiums. Let's draw another one. Now I can use my squiggly lines to make sure that everything is in good shape. And now I can redraw with my Lewis diagrams of the ions. And when you have more of one than the other, we try to surround the one of the littler number with the others. So oxygen in the middle, surrounded by 2 lithium. So I would draw it like this. Lithium, no dots anymore, +1. Oxygen, full, -2. Lithium, no dots, +1, and the 1 fell off the side there. I guess it wouldn't be incorrect to go up and down. You know what? If you were flying on a test and you did lithium, lithium, and an oxygen, I wouldn't mark you wrong. But in that crystal structure, that repeating structure of ions, they would spread them out in such a way that it would be 2 to 1, 2 to 1, 2 to 1, right? Formula for this one. Hands up, please. Formula for this one. Yep. Yep. Li subscript 2O. You've seen that before. It's like H2O, right? The 2 means we've got 2 lithiums. And the name. What do you got, Jocelyn, the name? Yeah, lithium oxide. Lithium oxide. Let's do some more. Oops. Oh, that's the last one. Wow. Maybe it's a good thing we talked for 20 minutes. I'd give you way too much time. Aluminum and fluorine. Again, don't wait for me. This is how you build your confidence. Then when I catch up to you and you've done it right, you can say, hey, I did it right before he did. That's awesome. Again, if you print yourself a periodic table, it makes life a lot easier, huh? Right? See? Unless I take it away from you.
No.
What do I need to do here in order to make the numbers work? Yep. 3 fluorines. Doesn't matter where you put the lone one, the one that's by itself. You could put it in any of the positions. It doesn't really make any difference. So again, for you guys, starting out, I have you put the nice little arrows to show where things are going. In this case, I would put the aluminum in the middle. And if you don't do it exactly like this, if you're up ahead of me, that's fine. Oh, look at what I did. Look what I did with that darn aluminum. And the eraser doesn't work. How am I going to fix this? And it's being recorded. It's horrendous. I'm going to cover those up with glue, as if they didn't exist. There we go. +3. And then it doesn't matter. I would just go around here. F. Now those are the ones we've loaded up here. -1. F. Could have went over the top. It doesn't matter. -1. Whoops. That's on the outside. 1 minus this time. Whatever. And I'm going to go up to the top here just to make it work. Just so I got more room. 1, 2, 3, 4, 5, 6, 7, 8. -1. Notice if you've done it right, the overall thing is electrically neutral. The +3 from the plus from the metal will cancel out all the minuses from the non-metal. Chemical formula for this one. Hands up. Chemical formula. Yeah, Connor. ALF3. Excellent. The metal always comes first. Name?
Aluminum chloride.
Yep. Aluminum. That's for my benefit. Fluoride. Again, for my benefit. The U. That's why you say fluoride. Or you won't make that mistake. Okay, you can see you've got some homework problems. I talked to you about the fact that there's an assignment. You've got about 20 minutes. Let me just show you where that assignment is online. So if we go to today's work page, there is formation of ionic compounds assignment. All right, there it is right there. And again, if you want to print, if you've already got it, you're filling in blanks, okay? And if you don't want to, you can just do it on a piece of paper, right? You know, it's complete all these things. And then on the end, I think I put a bonus one, aluminum and oxygen, all right? Okay? And that's going to be due, it's a good question. When's that going to be due? I'm going to give you some time to work on it tomorrow. We're not doing anything in terms of evaluation on Thursday. Thursday. This is due Thursday. Okay? All right. So I'm going to close that up. And I am going to stop the recording.